I have to finish with bad news. You know, like in old textbooks, we tend to romanticize. I can't help it. It was easiest to explain everything on unimodal map and on the 3-disk system. But when you ever try to solve a real physical problem, you'll find that this grammar is infinite. Almost always. Now what does that mean? That means that as I look more and more carefully, more and more time steps back, every so often I find some weird thing that's inadmissible. And that has to do with the fact that my Hamiltonian, my dynamical system, my PDE or something has some number of continuous parameters. And it's impossible to adjust all these parameters in such a way that the grammar that they correspond to is perfect. You know. So there will always infinite number of, but after you capture the main ones, they may be very long, these other inadmissible sequences. So the graphs will never be finite. And there is even worse news than that. Usually, this is a typical situation when we start working in more difficult problems like fluid dynamics, you know, quantum field theory, blah, 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 in high dimensions. We are actually totally clueless about symbolic dynamics. So all these nice examples I gave you labeled by zeros and ones, a set of letters, we usually don't have no clue what these letters are supposed to be. So what happens if I don't know anything? No qualitative dynamics. Now I don't know what the smiley for this is, but it's some expression like this. This is very typical. In that case, we have to be at least sure that we have found all the shortest periodic solutions. And if I found all the shortest periodic solutions, we haven't missed any, then we can do something that we call stability ordering. So, you know, the situation is that we have our, let's say, zeta function being equal to 1 minus sum of all pseudo-orbits, but there is a finite number. So we have generated a list of P1, P2 to some Pk, and we do not know how we're supposed to label them, but we know their stability, and we know the observable we are interested in computed on that periodic orbit minus the period of that periodic orbit. Then our intuition is that what's important when you're computing averages, you know, averages usually are something that's not very violent. So when I'm integrating some observable on a loop, it'll be roughly mean value of that observable times the length of the loop, which is the period. So these guys are not expected to behave much worse than the periods themselves, but these guys are falling off exponentially. So what we can do is we can write this as a sum of these guys, but only allowing lambda of the pseudo-orbit smaller than lambda cutoff. In other words, we include, if there is shadowing, if you know we don't have symbolic dynamics, maybe some of these guys shadow very nicely, but this rule will include everybody who is shadowing, because if our lambda cutoff is this, then you know this combination will show up because there'll be pseudo-cycles that are shorter. And we hope for the best. So try different lambda cutoff. Lambda cutoff has to be smaller or equal, presumably equal is natural, of your most unstable cycle. And that's something that's growing exponentially with the period of the orbits. So you hope that this is as good as it gets, at least with exponential error in time. So you hope that this is as good as it gets with the error of order of e to the minus Lyapunov exponent, so the mean expansion rate times your cutoff orbit. What you really do is you look carefully what observable you're interested in, what the convergence is, and you might find out maybe it's not important to keep track of stability, maybe it's very important to keep track of time. This requires some thought. But the message is that even when you don't have control, which we assume so far, of topological dynamics of your problem, and you don't know how to systematically, hierarchically organize it and put periodic points in all neighborhoods and ensure that you have optimal shadowing up to a given resolution or given number of steps in time, you can do a very good calculation nevertheless. So this is all, when you start computing periodic orbits and you start making corrections and predictions in terms of periodic orbit theory, there's a whole bunch of tricks which are in this book, but they're not really interesting. They're just experientially good ways to proceed about calculation. So this is it. Now we have cycle expansions. So we figured out how to herd cats. We just let them run, but the really important cats are the recurrent cats. They're called periodic orbits. So we capture all those and we track their trails and we capture all those which have come back after a certain number of nights, the discrete time recurrence. For each one of them, we have deterministic dynamics, so we can compute everything we need on that one. And now we have formulas that tell us how to compute expectation values of something that happens in infinite time from short time dynamics. And these formulas are totally non-intuitive in the sense that the reason why the course is taking so long to get to cycle expansions, I do not know any hand-waving way to give you these formulas. The hand-waving ways give you just stupid formulas because they don't include shadowing. So they're good enough to publish in PhysRev where you publish log-log plots, but shadowing is actually exponentially, super exponentially better. So it's qualitatively totally different game. You can ask yourself a few questions. Does it work? How well does it work? Why does it work? And can we do something with it? So I'll try to go to applications rather quickly.